L'Hopital's rule. Yeah. Little o. We use the limit way, so L'Hopital's rule. Yeah. Yeah. Here, let me just quickly, because we use L'Hopital's rule several times. Let us just do it quickly. Yeah. First, switch to continuous version. Two functions. Let's take derivative, numerator, denominator, and we know it's a infinity over infinity determinate form. So then, derivative. This is before we take derivative. Now, we just write root of x as power function, x to the 1/2 power function. Let's take derivative. Okay, two formulas. Then cancellation. Simplification, cancellation, simplification. Yeah. Okay, all right. After cancellation, simplification, you get this expression. Numerator 2, denominator natural log of 2 times power function x to the 1/2. This time, because it's not an infinity over infinity indeterminate form, we can take the limit directly. When x goes to infinity at the denominator goes to infinity. 2 over infinity, so the limit equals 0. Yeah. Yeah. Then we can go back. Yeah. So limit equals 0, so we have this conclusion. Log base 2 of n belongs to little of root of n. Conclusion. Okay? All right. Yeah. So another example. Yeah. After this example, the next one, I want to consider a little more general case. Yeah. So what's that? Show that natural log. Yeah. We know log base 2. Base actually not very important. Yeah. Base 2, we only require the base number greater than 1. Yeah. So the log base 2 or log base e, not very important in these questions. So here we use the natural log. Belongs to little of n to the d. So what's that d? D is a constant. But what is the range for that constant d? We only require d positive, greater than 0. That's all we need. D positive. Okay? Yeah. All right. And d, not necessary integer. D, not necessary integer. Okay? Yeah. All right. Yeah. L'Hopital's rule, take derivative, infinity over infinity, indeterminate form. Yeah. Then, L'Hopital's rule, natural log, just a 1 over x reciprocal function. Its derivative. Yeah. And the power function, its derivative d times x to the d minus 1. Yeah. Then simplification. Yeah. After this round, derivatives, we take simplification and get 1 over d times x to the d. It's not indeterminate form anymore, infinity over infinity determinate form anymore, so we can take the limit directly where x goes to infinity, because d is a positive number. So x to the d also goes to infinity, so the denominator goes to infinity, the whole fraction, its limit equals 0. Yeah. All right. So here you can see after we get this conclusion, yeah. So yeah. After we get this conclusion, so all these examples, yeah. After we calculate, yeah, we prove them. Then every time when you need to apply those results, you can use them. Use these results directly. Okay? Yeah. All right. So here, this result we may need to use many times later. Yeah. So this is important result. Yeah. So yeah, after these results, actually there are two results very important. Yeah. So I want you, memorize these two important results. The first one is this one. This one is important. Okay, the first one. The second one is this one. These two results, very important. Yeah. And in our homework assignment, number 1, our first big assignment, number 1, these two results, you will see several questions related to these two results. Okay? Yeah. And the hard part is, yeah, usually when you answer questions, you most of the time use your intuition, right? Intuition, try to understand. But these two results have some property. Your intuition could be wrong. Your intuition could be wrong. Yeah. These two results will have that kind of thing. Because your intuition, people use intuition, it cannot guarantee it's always correct, right? Yeah. Nobody can guarantee your intuition is always correct. Yeah. All right. So here, yeah. So let me show you. So first, these two results is correct. We can apply them directly. Then, let me try to challenge your intuition. Challenge your intuition. Okay? All right. First example. Okay? All right. Compare these two functions. The first function, n to the n to the 1/millionth power. Is that function pretty big? N to the millionth power function. Okay? Compare this function and another function. Okay? All right. So the second function is 1.0000001 to the nth. Just slightly greater, the base number slightly greater than 1. Yeah. So many zeros. Okay? Very close to 1. Yeah. But raised to nth power. Okay? All right. Now I ask you to compare these two functions. Which one eventually faster? Which one is the final winner? Okay? Final winner. Yeah. At the beginning, one is slower than the other, right? So we know, beginning it's not that important. Yeah. We want to see who is the winner at the end. Yeah. Based on intuition, which one you feel it's larger? Right? Think about that. Which one is larger based on your intuition? Okay? Which one you feel should be larger? Okay? Yeah? Think about that. So, because, n raised to 1/millionth, it's so big. Even we put 2 here, it could be a huge number, right? Yeah. So big. Okay? But this one, the base close to 1, so many zeros, very close to, you multiply n itself n times. How do we have no idea how big it is, right? We have no idea how big it is. Okay? So then I ask you compare which one would be the event, final winner. Final winner. Do you think the first one should be the final winner? The first one should be the final winner or the second one?
I think conditionally, it could be the first one. Like if n
Yeah.
is greater than 1, greater than 1.
Yeah. And n could be very large. N goes to infinity. Basically, n goes to infinity. Okay? We compare where n is extremely large, goes to infinity. So, yeah, most of you, by your intuition, the first one will be larger. But look at what is our result? If you agree, so you have no problem with the first result, right? That D is 1 million. That D is 1 million. The A, we choose 1.001. It's okay, right? But our result tells us the first function belongs to little of second function. Which one is larger, right? You apply the first result. Which one is larger? Okay? Yeah. So here, I just want to show example. Sometimes our intuition may not be reliable. So if we prove a result rigorously, you should be very confident to use our result. Okay? Yeah. We prove it rigorously. So you should have the confidence on our proof. Apply it. Even if it's against your intuition, apply it, okay? Even if it's against your intuition. Right. Then, the second one, another example. Second one. Okay? This time we compare natural log function, the first one, and the second function, n to the d. Remember, d only needs to be positive number. Can we consider n to the 0.0000001? Okay? Right? Yeah. It looks so small. Yeah. N to the 0, so many 0 after decimal point. The same question, these two functions, which one would be the final winner when n goes to infinity? Yeah. So your intuition, we know natural log, although natural log is not as big as n function, but natural log still goes to infinity. Right? Natural log still goes to infinity. Okay? Natural log function, if you draw the curve, it's like that. Still goes to infinity. Okay? All right. But the second one, n to the 0 point, so many zeros after decimal point. Yeah. It looks like very small number. So you take the root. Okay? You take 1/millionth root. Yeah. This one, like you take 1/millionth root of n function. When you take 1/millionth root, by your intuition, it looks like it goes to 1, right? Approaches, yeah. You take root, 1/millionth. Approaches to 1. Yeah. Although it's not 1. Okay? Yeah. Very flat. The curve very, very flat. All right. Yeah. So if you want to use your intuition to make the decision, yeah. So it's very likely you will choose the first one, the final winner. But look at our conclusion here. This is our conclusion. The first function belongs to little of the second function. Yeah, we prove it. It's correct. Okay? Yeah. So if you use our proved result, then your answer will be different. Okay? Yeah. So in the first assignment, be careful. All right? Yeah. When you see those similar questions, be careful. We have some results we proved in class. Okay? Yeah. All right. Yeah. Let's move to the next topic, C.4. the bubble sort. Yeah. In this one, so we do sort again. Yeah. So we try to find a second solution. Actually, the bubble sort you already learned before, but here we want to look at using a different concept. Yeah. From the problem solving point of view, so we want to find a different solution. Yeah, so this bubble sort. Okay, all right. So let's solve the sorting problem again. Yeah. So our previous solution is selection sort. So this time we want to find a different solution. Yeah. Yeah. So the same problem, we want to use different solutions. Yeah. Yeah. So how do we do that? So usually when we solve a problem, we need to based on a critical property. Yeah. The critical property we used in our selection sort. Yeah. So let me recall the selection sort. The critical property we used in that solution is every time when we find the minimum of the array, we can put that element in place. That's the critical property. If we can find the minimum of the current array, we can put the one element in place, or one more element in place, and so on. Okay? Yeah. That's the critical property. In place, minimum, and in place, these two keywords. Okay? Yeah. For the solution. Yeah. All right. This time we want to solve this sorting problem differently, so we need to find a different property, different critical property, so that we can get a different solution. Yeah. I want to show you that process. All right. So let's look at this diagram. Okay, this diagram. Yeah. So this time we take a different view. Yeah, we need to adjust our understanding. We look at the same problem in different angles. Different angles. If you use same angle, you get the same solution. Here we want to change our view angle so that we can get different solution. Yeah. All right. So let's look at a pair of elements like this. A pair of elements. This time, this is our view angle, okay? A pair. We just select two elements in the given array, and we want to look at their relationship. What's the relationship between arbitrarily selected two elements in the array? Yeah, that's our view. Different, quite different from our first solution. Yeah. All right. If you look at it like that, then two possibilities. Yeah. Yeah. In order and out of order, right? Yeah. If you only look at two elements in a pair, if the first one less than or equal to the second one, that's in order. Ascending order, yeah. Ascending order is the relationship we want to have, right? In order, okay? Then the other one out of order, the first element is greater than the second element. That's the one against our requirement, right? Yeah. Our goal, we want to get all elements in order. But this one, this pair, out of order. So, you know, out of order, that means it is relatively far away from our destination position, right? Our destination position, yeah. Yeah. So these two states, in order state and out of order state. Yeah. Now we want to find a solution based on this property, this special property. Okay, in order property. Okay, yeah, this property. Yeah. All right. Then observation for critical property. So yeah, if the array is not sorted. This property. Yeah. Let's assume if an array is not sorted, then there must be two adjacent elements that are out of order. Can you see that? If an array is not sorted, there must be two adjacent elements that are out of order. This is the critical property. If we can see that, then we're halfway to our final solution. Halfway of our final solution. Okay? Yeah. All right. Yeah. You can use the contrapositive thinking here. Contrapositive. Yeah. If there is, the contrapositive thinking here, if you assume any two adjacent elements are in order, then the whole array must be in order, right? Yeah. Contrapositive. So if it's not true, if we cannot find any two adjacent elements that are out of order, that means any two adjacent must be in order, in ascending order, in order. Then, by the transitivity property, the whole array must be in order. Yeah? Then our assumption is incorrect. Our assumption is the whole array is not sorted. The whole array is not sorted. Yeah. So if we use that argument, contrapositive argument, we can see this property. Okay? Yeah. So this is a critical property. Yeah. All right. Yeah, so here I give you the reference of this algorithm in our textbook. Yeah. Then, next we want to make our solution, but before we go there, we want to use a concept called inversion concept. Yeah. In our discussion, just like we use the in-place terminology in our previous solution for easy discussion, here we use another concept for easy discussion, inversion concept. Yeah. So what's inversion here? Yeah, let me give you the definition of inversion. A pair of element A sub I and A sub j is called an inversion if this property is satisfied. If I less than j, then A sub I is greater than A sub j. That's inversion. Okay? Yeah. The order of the subscript is different from the order of their corresponding element values. That's the inversion. Yeah. If they have the same order, it's not an inversion. Okay? So they have opposite order. Yeah. The subscript order and the element value order are different. That is an inversion. Yeah. So that concept. Okay, inversion. All right. Then, now, if the array is not sorted, so now let's try to use the inversion concept to understand if a given array is ordered or not. Yeah. Use inversion concept to understand. Yeah. So if the array is not sorted, there must be an inversion, right? Is it true? If an array is not sorted, then there must be an inversion. Think about that. Yeah. So you can find a pair that is out of order, right? Yeah. You can find just an arbitrary pair. Yeah. You check. All the pairs, there must be one of them, at least one of them, that is out of order. Then the array is not sorted. That simple property. Okay? Yeah. All right. Another one, if the array is not sorted, there must be an adjacent inversion. Look at that. We just add an adjacent word. If an array is not sorted, there must be an adjacent inversion. Yeah. So this statement, the same as our previous one. Okay, remember? Adjacent, out of order. We just use different terminology. Okay. The previous one, we didn't use inversion concept. The second one, yeah, after we introduce the inversion concept, we just use the inversion terminology in the statement. Yeah. All right. So here you can see, yeah, these two statements, both true, so we can treat as the property, both true, yeah, but yeah, the first one, the first statement, we use the global inversion. Global inversion. Yeah. Second one, we use the local inversion. Okay, global inversion and a local inversion. Okay, yeah. All right. So they are different. Yeah. Although these two, both statements can help us to check if a given array is sorted or not. Yeah. But we know checking local inversion much easier than checking global inversion, right? Global, you need to, consider all the possible pairs, too many pairs, large number of pairs you need to consider. Local inversion, much fewer pairs to consider, right? Yeah. Yeah. So much easier. Yeah. Yeah. That means our algorithm should be based on the local inversion, not global inversion. Okay? So local inversion, yeah, to make our new solution. Yeah. All right. Yeah. All right. So the idea of the new solution is, let's check all the possible local inversions or adjacent inversions. If we can find one, let's swap two elements to remove that inversion. Swap two elements to remove inversion. Okay? Whenever we see one local inversion, an adjacent inversion, we just do swap operation to remove it. If we can remove all the local inversions, adjacent inversions, then we get it already sorted. That's the idea. That's the, solution idea. So let's implement this idea. Yeah. The implementation, pretty straightforward. Yeah. All right. Yeah. Yeah. From global inversion to local view. Yeah. Global view. Yeah. So we know global view usually harder, local view usually simpler. Yeah. All right. Now swap operation. Yeah. So we need to use swap operation to reduce the number of inversions. If we can reduce all the inversions, eliminate all the inversions, then we get already sorted. Yeah. That's the idea. Okay? Implementation idea. Remove all the local inversions by local swaps. Yeah. All right? Yeah. All right. So the first step, let's start from the first element for each scan. Every time we do one scan, starting from the first element, but we only check two adjacent pairs and see if there is an inversion. If there is one, swap. If not, move to the next adjacent pair until we reach the end. That's for one scan, the first scan. Okay? After first scan, can you get what will you get after the first scan? Okay? After we first scan from beginning to end, which element is in place? Can you tell me after the first scan which element is in place? Can you see that? At least one element is in place. Which one? Can you see that? Is the first element in place? Is the second element in place? Is the third element in place? Yeah, yeah. After we complete all the swaps, but only first scan. Okay, first scan, not second scan. We need to do many scans. Okay, the first scan. Or is the last element in place? Think about what? After we do one swap, we switch the order, right? The second one is larger than the first one, right? The second one is larger than the first one. Think about that. And we do all the way from the beginning to the end. Which element is in place after you? Last one. Last one is in place. Last one because it corresponds to maximum. Maximum element always move to the later position, right? Next, always move. Yeah. Next, largest element always move. Yeah. So there. So last element is in place. After that, we do second scan. Okay. When we do second scan, we can skip the last one. We do not need to touch the last one. It's already in place, so we don't touch it. Yeah. So we get another element in place, second to last. Second to last one in place. Okay? All right. So do swaps one by one from left to right. Yeah, if necessary. Because sometimes we do not need to do swap. Okay? If in order, we don't do swap. If necessary. Okay? All right. Stop at the first in-place element. Yeah, because every time we put one element in place, at least one element in place. So if we put an element in place, why we touch it again? So we should stop before we touch it, right? We can stop before we touch that in-place element. So we can reduce the problem size. Each scan, we process a subarray with smaller size. At least we reduce size by one, right? By one, okay? And finally, we put all elements in place. Finally, we put all elements in place. So we are done, okay? Yeah. So this process, because it looks like a bubble moving, right? Yeah, bubble moving. So people call it bubble sort. Okay, your swap operation. Okay, yeah. So that, yeah. So all right. So there is one element in place for every scan. So we know that's the last one. The in place element for each scan appears at the end of the current array. Okay, yeah. Yeah, right before the previous in-place element. Yeah. So the current array is a subarray that excludes all the in-place elements. Yeah. All the non-in-place elements. Here, yeah. To be more precisely, I want to add all the known. Yeah, because some elements unknown, right? Some elements also in place but unknown. But these elements, they are in place, and we know they are in place. Yeah. Other elements, although they are in place, but unknown. Okay? Yeah. So we can separate like that. Yeah. Yeah. Known element, in place elements. Yeah. All right. Visual imagination. Yeah. The swap looks like a bubble moving to the right, yeah, from left to right. Every scan from left to right. Yeah. So this operation. Okay. Yeah. So then people call it bubble sort. Yeah. All right. Then, after we get the solution, yeah, we want to count the number of comparisons. How many comparisons we need? Yeah. Yeah. All right. So efficiency analysis is similar to that of the selection sort. Yeah. Because we consider all the possible pairs. Yeah, so you can count the number of comparisons. So the same as we count the number of comparisons in the selection sort. Yeah. Here, so what is the last question for this topic? What is the basic operation? Yeah. Remember, we talk about basic operation in an algorithm. Which operation is used the most in the algorithm? That's the basic operation. Okay? Yeah. Yeah. Most commonly used operation. And in this one, we have two operations we can consider. One comparison. You need to do comparison to see if you have inversion. Another swap operation. Okay? Yeah. Here, based on your understanding, do you think we should choose comparison as the basic operation or the swap operation as the basic operation? Which one we should choose here? These two. Comparison and a swap. Which one is used more often?
I assume comparison.
Yes, comparison, not swap. Comparison, yeah. Because imagine if the array is already in order, then there is no swap, right? If the array, the whole array is already sorted, then there is no swap operation. But you still need to do the same number of comparisons, right? Because you need to check all the adjacent pairs. Yeah. Even if they are all in order, you cannot miss anyone. You still need to check all the possible orders. Yeah. 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 But some students, their textbook gives an improved algorithm to reduce the number of comparisons. Yeah. So there is a improved version. Yeah. That is, every time when you do the scan, you count the number of swaps. You create a temporary variable to count the number of swaps. If the swap number is 0, that means it's already ordered. Then don't do the next scan. So the improved version is, you create a variable to count the number of swaps. As soon as you see the number of swaps equals to 0, then you already get it sorted, right? So you can stop. That's the improved version. Yeah. You can improve slightly, yeah. 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 In a textbook, that version is there. Okay. Yeah. All right. So we finish this topic and this bubble sort topic. Yeah. All right. Next, I want to switch to module 3. Yeah. All right. Yeah, okay. Module 3, recursive algorithms. Part A, introduction to recursive algorithms. 8.1, first view of recursive algorithms. Yeah. I think you have some experience about recursive algorithms, but in this module, we will spend a lot of time to understand this recursive algorithm. Yeah. Yeah. All right. First, recursive thinking. Yeah. First, we want to understand why we want to study recursive thinking. Recursive thinking, yeah. Because usually, yeah, for an ordinary person, if he or she does not have the algorithm training like us, okay, yeah, ordinary person, yeah, that person may not have the recursive thinking. Okay, yeah, you need to have some training, yeah. Otherwise, yeah, because people usually they like to have the straightforward thinking. Yeah, this recursive thinking, kind of indirect thinking, indirect way. Yeah, not direct thinking. People are used to direct thinking. Okay, so you want to see, you want to feel about it. Yeah. Recursive, so something is look like hidden. You cannot see. You cannot see it. So here, let's look at this special thinking, recursive thinking. For our computer science people, it is very important. So we need to study this recursive thinking first. So why recursive thinking is important in problem solving? So we're used to straightforward, non-recursive thinking in problem solving. Because it's easy to understand. But some problems can be solved both non-recursively and recursively. Most of the time, you can have these two different types of solutions. Recursive solution and a non-recursive solution. And each one has its advantage and disadvantages. All right. Then the importance why computer science people, we want to learn the recursive thinking because it is very powerful. This problem solving method is very powerful. We want its power, okay? Its strength, its advantage is its power. So we will try to understand the power later. All right. Some relatively, what do you mean the power? The power in problem solving, so you can solve relatively hard problems by its power. Okay? Some relatively hard problems can only be solved by recursion. So here I put a parenthesis around that only, because there is some argument about that. People can argue. All right? So here I put a parenthesis. Be solved by recursion. Or we can say in this way, if you do not use the recursion, some problems are extremely hard to solve. So we will see some such examples. Extremely hard to solve without using recursion. All right. Before I show you the power, I want to compare these two types of algorithms. One, iterative. When we say iterative, that means non-recursive. So the problem, we try to avoid recursion. Okay, sometimes people like to avoid recursion using iterative algorithms. So when you see iterative algorithms, that means non-recursive algorithms. And it has advantage. It has its own advantage. So I will explain that. Non-recursive, it has its own advantage. The second one, recursive. Recursive, the biggest advantage is its power. So powerful. All right. Then, the advantage of the iterative, less resource. It uses less computing resource. All right. Disadvantage, harder implementation. The second one is disadvantage, harder, less computing resource. So what resource you are talking about? Here, the main resource we are talking about here, main memory. RAM, okay? Main memory. We know every implementation of a computer algorithm, you need to use a lot of memory resource. Okay? So you load your data into the main memory, all the instructions, execution, all executed, from main memory. So the resource, main memory resource, is very precious. Okay? If you waste too much memory resource, then your algorithm could be very slow. Very slow. So we want to save as much main memory resource as possible. Yeah. So here, it's important. Memory resource is important consideration in our algorithm design. Yeah. All right. So iterative version implementation of algorithm, it can save a lot of main memory resource. Okay? Yeah. So then, recursive algorithm, you can, although I do not say explicitly, yeah, but you can understand in this way. Recursive algorithm, we need to use more main memory resource. Okay? Yeah. Later I will explain more details about main memory resource. Yeah. Not here, later. Later I will explain that part. Yeah. Okay? Yeah. All right. More resource, but easier implementation. Implementation point of view, yeah, comparing with the iterative algorithm this way, yeah, the coding, yeah, you can write much simpler coding, implementation code, yeah. All right, yeah. All right, yeah. Yeah. Next, yeah, yeah, because we finish today, I want to, yeah, here we only have 10 minutes. I want to talk about our first simple example in recursion. Yeah. Calculate the factorial. Yeah. We know the definition of factorial and the formula, and we do not need to use recursion, right? Yeah. Typically, we just use the iterative way. We write a for loop, we can calculate factorial. Yeah. But here, I want to talk about the basic structure or the basic understanding of the recursive thinking using this simple example. Yeah. All right. So given a non-negative integer n, find its factorial n factorial. Yeah. All right. Yeah. This very simple example, but this time, yeah, here, method 1, iterative. Yeah. Then method 2, we convert it to recursive way. Yeah. Iterative, we just apply the definition of factorial directly using a for loop, right? Yeah. But when n equals 0, yeah, there is a special value of factorial. When n equals 0, we assume 0 factorial equals 1. That's our assumption. 0 factorial equals 1. Now, can you see why we make this assumption? Is it a reasonable assumption? 0 factorial equals 1, not 0. 0 factorial equals 1, not 0. Do you feel strange a little bit? Yeah. How can we understand 0 factorial equals 1, not 0? Yes, like that. But still a little hard to comprehend, right? Yeah. So empty, you have nothing. When you have nothing to do, you have 1 left, right? By default, you have base 1 left. Something like that, but still, we feel not very solid, right? Still a little shaky, right? Yeah, this understanding, a little shaky. Yeah. Later, I will use a rigorous way to explain this point. Yeah. We can rigorously derive 0 factorial must be 1. Yeah. All right. Yeah. So next, implementation of this. Yeah. We just make a 1 simple for loop. It's done. Yeah. So simple. Yeah. All right. Then method 2. Now I want to, although it's unnecessary, but as a learning process, so we want to use the recursive way to understand the, from another view of angle to understand factorial function. All right. Idea. So here, this is also a general problem-solving approach. Yeah. So this idea gives you a general problem-solving, you heard of one commonly used method called divide and conquer, right? Divide and conquer. Yeah. So here, we apply the idea divide and conquer. Yeah. Yeah. Our next module, module 4, we will devote the whole module to divide and conquer. Yeah. But here we already used the idea a little bit. Yeah. So these two modules are most important. Module 3, recursive algorithm. Module 4, divide and conquer. These two are two most important modules of this class. Yeah. Yeah. Also, module 1 also very important. Yeah. 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 Oh yeah. Actually, we can say everyone is important. Yeah. But yeah. 3, 4, 1, 2, and 5. Yeah. All right. Divide and conquer. Yeah. 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 So the idea behind that divide and conquer, so why it's so effective? Why divide and conquer method is so effective? Yeah. First, the problem is easier when the size is smaller. Yeah. Usually, remember I explained the principle last time. The principle, okay? Yeah. So the problem is usually, most of the time, easier when the size is smaller. So we want to break the original problem into smaller subproblems. Yeah. Divide, conquer. Yeah. Easier to conquer. Yeah. After you break it, divide, easier to conquer. Yeah. When you work on a problem of current size, assume that the problem of smaller size has been solved. Yeah. Remember, at the end of the last part, before the break time, I talk about that approximate way problem solving. Yeah. Here, you can understand that way, yeah, because the smaller size, that one, we use it as the approximation of the original problem, right? But we already solved easier version of the original problem. Then, next step, we just bridge the gap. There is a gap. Okay? Yeah. Smaller size, original size, between these two sizes, there is a gap. So we want to find a way to bridge that gap. Yeah. So that's the second step, point. Third one, fix the gap or bridge the gap through a recurrence relation. Yeah. How do you address that gap, right? Yeah. Here we use the recurrence relation to address that gap between a smaller size problem, current size problem. There is a gap. That gap can be represented by a recurrence relation. Okay? Yeah. Yeah. That's the reason these three steps, after we derive the recurrence relation, so we can use that divide and conquer approach to write its implementation, so we can solve a very hard problem in some simple way, this way, recursive way. Okay? Yeah. The original problem could be very hard. Yeah. But we use this three steps, 1, 2, 3, we can solve a very hard problem. That's the idea, basic idea. Yeah. Yeah. Basic procedure. Yeah. But you need to have a lot of experience to get used to this whole problem-solving approach. Yeah. Some experience. Yeah. All right. Yeah. Next, let's use our method number 2 to solve it. Okay? All right. Yeah, let me just stop right here because we only have 2 minutes. Yeah, so I don't want to, talk about in the middle, then, stop next time. You already forget the first a few steps. Yeah. So let's start from the very beginning of our method number 2 next time. Yeah. All right.